So the first one in the link is the one for today, is that right?
Yes.
Okay, okay. We are live. Okay, so I can see the thing here. It's it's not showing any video yet, though, right?
No, it should. Wait, this is the one. No, it's just refresh. It's live for him. You watching? Yeah, it's the one.
Where's the guy? Is he?
No, he's still there.
Okay. The Facebook will do from here. It's also not working great. all the tech stuff is not working great. We'll figure it out. I think it's okay if we start a little bit late. I don't have half an hour's worth of things to say here, so yeah, so I think it's okay. Yeah, no, exactly. I'm just going to thank everyone. It will take 10 minutes, so I think it's okay if we start a little bit late. We can still start the lectures on time. Yeah. So I've told them on the Gazan side, but okay. So let me start the video call from here. Okay, let's check. Huh. It's clearly working.
We have a Ethernet cable.
It doesn't work on this computer. So.
Maybe that don't go, right?
Yeah, no, I think it just doesn't work at all.
Hello.
I think this is the wrong link. It must be, right? Yeah. It's day one, but it cannot. Something is wrong. It must be the.
Do you have different browser?
Yeah. But they also don't see it from the Gazan side. I think the link that you just clicked on, is it the same one that Abdallah sent?
Just go to the go back.
Go back
to the browser.
Yeah.
Click on the yeah. This one.
Yeah, this one will do.
This one is working.
Yeah.
Okay.
This one.
Not yet. Wait. Let's get the connection with them first. I think we'll start slightly late. Let's get the connection with them first on Gaza, and then we should make this go live as well. Okay. Yes. Okay. Hello. Okay. Great. Hi. Okay. We'll start in 2 minutes, okay? Yeah. Okay, we're starting in 2. Okay. Are people inside? We'll start in 2. Can you, everyone, this is Hannah. Can you monitor them as the thing goes on? Yeah. Okay. All right. So who's here? Are we all here? Okay. Now we start the Facebook, and then we're good to go. Can you set up the Facebook Live from your iPad from the Scientists for Palestine page? One second. I think we are pretty much good to go. Oh shit. We're not using this one anymore. That's good. Yeah, we're not. Oops. Yep. Ready to go live? Did you put some text in the thing? This is on the Scientists for Palestine page. Did you put some text? No. Can you put just a little bit of text? Just say day 1 of the. Yeah. Palestinian Advanced Physics School. Yeah. Sorry, opening ceremony. Go live. Okay, hello everyone. Good morning. We're sorry for the slight technical delay. So welcome. My name is Nabil Iqbal, and I'm here to welcome you to the 3rd Palestinian Advanced Physics School. Okay, so these are just going to be a few opening words to tell you what's going to happen. So this is the 3rd Palestinian Advanced Physics School. You can see here pictures from the first 2. The first one was held at Arab American University in Jenin in 2016, and the second one was held a year later in 2017 right here in Birzeit in this very room. So basically what's going to happen is we're going to listen to lectures in topics in contemporary physics. But what does that involve exactly? What that really means is you're going to hear lectures from absolute world-class experts in physics. So let me just give you a brief introduction to the different people who will be lecturing throughout this school. We have Professor Rafal Dunin-Borkowski, who is a world leader in the field of electron microscopy, and he will be telling us about atomic resolution electron microscopy in 2 lectures. We're also extremely happy to have Professor Beata Kardynal, who will be telling us about semiconductor quantum optics, and they're both based at the research center in Jülich in Germany. Okay, moving on, we have some more lecturers. I'm very happy to say that we have Professor Anne Christine Davis, who is an expert in cosmology, and she'll be introducing us to cosmology, which is basically the field of study of the entire universe, in a lecture series called Topics in Modern Cosmology. She's based in Cambridge University. And finally, I'll mention that we had been hoping to have a different lecturer, but he did not get a travel permit in time. And instead, you have me, And I am not quite as illustrious as a scientist as the other three, but yet. Thank you, Anne. But in any case, I'm extremely happy to tell you that I will be giving you a brief and gentle introduction to the area of theoretical physics that is called string theory. And I am a junior faculty at Durham University in the UK. Okay? So all of this is lecturers. But of course, the school is not built out of lecturers. The real glue of the school is the students. So where are the students coming from? The students are coming from many different institutions. The three biggest ones in the West Bank are Al-Quds, An-Najah, and of course our hosts at Birzeit University. Okay? And also, we have several participants who are coming from Gaza. They are following us on a Skype link right now and over the live presentation. Unfortunately, though we had 14 applications that we approved, no one got a travel permit in time to come to the school. And as such, our Gazan colleagues will be following us via Skype. Let me say a few words about the people who are making this school possible. This school is sponsored by three different institutions. There is the ICTP, the International Center for Theoretical Physics, based in Italy. They're contributing to this school. There is CERN, the Massive Accelerator Physics Laboratory in Geneva. And of course, there are hosts at Birzeit. So in fact, this is a very good time for me to turn the floor over to Professor Abdallah. He has been the main organizer from the Birzeit University physics side, and now he'll say a few words about the school.
Hi all. Let me first welcome our students from all over Palestine, like from Birzeit, An-Najah, and Al-Quds, and of course from Gaza. As you can see, all of them are very young and motivated. So we worked very hard to have like different experts in physics from like working on different time and spatial scales from applied to theoretical physics. I hope that it will be very useful and will motivate many of you to pursue like your graduate studies in one of these fields or open your eyes to other fields. Of course, I would like to thank our guest lecturers from Jülich Research Center, Rafal and Beata. And of course, we will have Ghalib Natour, who will introduce you about opportunities from the Palestinian German Science Bridge, which gives opportunities to pursue like a PhD in Germany, or you can finish your master work degree in collaboration with the Palestinian supervisor. Of course, in cosmology, we have our guest Anne, which will address the very large scale physics. And I would like to thank Nabil for his efforts throughout the previous many months, so thank you very much. And I wish you a very fruitful and enjoyable school. Thank you.
Thank you. Okay. So I'll just say a few more words before we begin. Let me tell you a little bit about the group that is organizing this. So there's a larger group organizing this, which is called Scientists for Palestine. And we are a group that has members that are spread all across the world. There are roughly 25 of us now. And our goal is really to promote scientific education and research in Palestine. And there are two members of this group who I have not talked about yet, so let me just say a few words about them. They are Hannah Dalglish, who is based in Liverpool, and she's right here. And there's, of course, Sameh Othman, who is based here in Birzeit, and he's in the back over there. The two of them have put a huge amount of effort into making this school happen, and they're here, so you can hang out with them as well. Okay, so that is all that I have to say about the sponsors and the organizers of the school. Let me now tell you a few practical details about how the school is going to work. So first of all, the timetable, you all have received a copy of it. It's over here. There may be some small changes to the timetable. We'll try not to, but no matter what, the latest timetable will always be on the website right here. So I'd say take a look at that, and we'll announce any changes. but the timetable is right here. You can see it. So what are you actually going to do, the students? So what you're going to do is the following. You are going to, number one, attend lectures. You listen to all these lecturers tell you about things about physics. But also, you will take part in discussion sessions. Periodically, we will break into smaller groups where you can discuss things, you can ask questions and discuss things more in a one-on-one way with the lecturers and the organizers of the school. Another important thing is you will attempt problems. In particular, starting soon, we're going to start distributing to you problems based on the lectures, okay? And we'll distribute them in the lecture and we'll post them on our website. And you should attempt these problems. A subset of these problems are going to be homework that you have to attempt, and then you have to hand it in at the end of the day on Wednesday, okay? So you don't get to just listen. You really have to work out problems and hand in the homework. And if you hand in the homework and make a serious attempt, then at the end of the school on Thursday, we will give you a certificate of attendance at the closing ceremony, okay? So everyone has to do the homework, basically. Okay? And those are the practical details. Here are a few more fun details. We are extremely happy to say that Anne is going to be giving a public lecture to the community at large on the topic of the accelerating universe. This is going to be on cosmology, but a different aspect of it than the parts that she's going to tell us about. It'll be at Ramallah in the A.M. Katan Foundation. So everyone should come, and everyone should bring your family and your friends and everyone else, your colleagues, anyone without a physics background necessarily, who'll just be interested in learning about the universe and how strange and mysterious it is. That'll be on Monday, tomorrow at 6 p.m. And next, there's also a social dinner tomorrow at 7:45 p.m., which is open only to the registered participants of the school. And basically, we will eat and have fun at the Siran restaurant, also in Ramallah. Okay, those are all of the details that I have. And now I'm going to turn the floor shortly over to Anne, and we'll get started on the actual physics part of this. Thank you, everyone. Okay. So we'll start in about 5 minutes. We're just going to check the video and the technical stuff again. Give me 1 second. Start at the usual time because I finished talking a little bit early.
Oh, okay. Okay, so I don't start yet. Oh, okay, it's early. Before we start, can I make a suggestion? There's quite a lot of you sat over there. The screen is there. There's a little whiteboard here. Just in case anything needs to be written on the whiteboard, can you see over there? Oh, okay. I was going to suggest you might want to move over a little bit. But you don't have to. Oh. Yeah. Some of them are moving. Is Gaza there?
Gaza's on Hannah's.
Gaza's on Hannah's, yeah.
Are they say they can't hear anything.
Sorry?
They say they can't hear anything. No, it should be coming through the YouTube.
Should it be coming from me?
Yeah.
From me? Gaza, can you hear me?
But I thought that they are doing the sound through that. Because the YouTube, we're doing the Gaza is following through the YouTube. Yeah.
Ah.
So the sound should be going through the YouTube, not through the Skype, is so that they can ask questions.
Oh, I see.
It's
Right.
not meant to go through there. Yeah.
But they can't hear it.
Okay, sorry everyone. We're going to start at noon. We're going to try to fix the sound for our Gazan colleagues. So we'll start in 7 minutes. Till then, yeah, hang out, and we'll start exactly at noon again. Okay.
Yeah. So Gaza can't hear.
Yeah, Gaza can't hear apparently.
Oh, that's unfortunate.
Unfortunate, yeah. So let's see here. Yeah.
They wrote yes.
There is a yes. I don't know if it's in response to what you were saying, but there is a yes.
Let's not follow ourselves carefully on the YouTube. So.
Hello, Gaza. It's Anne here. I'll start lecturing in a couple of minutes. If you can hear me, can you type yes? You're not Gaza, you guys. Gaza, can you type yes? They type no? Oh, they can hear us. I can talk? Hello, Gaza. Anne here. I will be lecturing soon. Is it coming through, the sound? Yes? I can't see it at the back.
Maybe it was just me then.
You were pretty loud, though.
I thought so. Never been accused of being too quiet before.
No. There was an updated one this morning with a sort of extra lecture in. Yeah, yeah, that's it. Yeah. Okay. Don't know. Okay. I think so.
Okay, so we're very happy to have Anne will tell us about cosmology. Anne, take it away.
Okay. Well, thank you very much for allowing me to lecture here. Years and years ago, when I was young, I was at Princeton at the Institute, and Edward Witten said that anyone who ever visited Israel should also visit Birzeit University. Well, this is my first time visiting Birzeit University. Actually, it's the first time I've visited Israel, so I guess I'm following Edward's advice. It's a pleasure to be here. I'm talking on cosmology. There was meant to be a lecturer talking on gravitational waves who couldn't come because he didn't get a visa in time. He's from Malaysia. And so I thought that rather than doing 4 lectures on cosmology, I would try to do something on gravitational waves and black holes, because they've been really so topical. So let's see if I can get this to work. I'm not good with technology. So I'm going to have 2 lectures on cosmology, and I'm going to introduce black holes in the 3rd lecture, and can I get rid of that little, I think so, but I don't know how to do it. Ah. Okay. There's something wrong with this, isn't there? Okay, good. So I'm going to try to do an introduction to black holes and gravitational wave radiation. And I should say I will be doing this without a knowledge of general relativity. So I'm just assuming you know nothing about general relativity at all. If you do, then that's great. And I don't really know the timing either. So our universe is expanding. This was noticed by Hubble and actually people before him. Hubble noticed in particular that the galaxies that he could see were moving away from him at some sort of constant velocity. And so Hubble formulated a law that the velocity they moved away, was some constant h times the distance. Now I've put h as a function of time because we don't actually, well, it could be a function of time. What we do, we call h naught the Hubble's constant today. So if you see something like t naught, that means the time today. The little naught says today. H naught, the Hubble constant today, we measure as about 70 kilometers per second per megaparsec. Megaparsec is an astronomical unit. A parsec is defined as the distance at which one astronomical unit subtends an angle of 1 arc second. So this is the formula here. It's 3 times 10 to the 12 kilometers, and the astronomical unit is the distance between the Earth and the Sun as it goes around the orbit. Of course, depending on the precise nature of the Earth's orbit, its actual distance will vary slightly, but they have the approximate astronomical unit there. And H inverse, the inverse of the Hubble constant today, gives us approximately the age of our universe. It's 13.77 billion years is the current estimate of the age of the universe. So if the universe is expanding at constant velocity, for our purposes, this isn't very good to actually measure distances, properties of galaxies. So what we do is we extract the time dependence from the distance. So rather than having r as a function of time, it's moving away, let's write r as a of t, which is called the scale factor, times x. And x is the co-moving distance which just goes along with the flow. If we define r in this way, then this Hubble constant is a dot dA by dt over a. And we define a at our time today, a naught as a of t naught. It's 1 today, and hence we normalize our units. So this is a diagram of the Hubble, well, this is the diagram of the velocity that objects are moving away from us times their distance, and they're an approximate straight line. And we sort of measured this from the redshift of galaxies. There's still some dispute on what the Hubble constant is today. I had it down as 70 on the previous transparency. Here, this one it writes down as 64, and it depends on the objects you're measuring and how accurate the measurements are. So I'm just going to say approximately 70. So this is a Hubble diagram where you're plotting the velocity. You could call, say, the velocity the objects are moving away, or recessional velocity, times their distance. And as you say, I've got this going out to 50 megaparsecs. Mega is, of course, 10 to the 6 parsecs. And I had previously at 1 parsec was 10 to the 12 kilometers. So that's an enormous distance. it gives you an indication of the scale we measure. Okay, now I don't know how many of you have done special relativity. How many have done special relativity? Some of you. Okay, so some of you I would be telling you what you know, and some not. In physics, we are used to writing a 3-vector. So we write down the vector x, which is x, y, and z. When we go to relativity, we write down a 4-vector. The fourth component is the time. To make it dimensionally correct, it's the speed of light times the time. So now we write an element as a 4-vector, dx squared. Oh, here we go. Now we've got dx squared as dx squared plus dy squared plus dz squared. Now we go to what's called the invariant distance in space-time. And I write it as ds squared. Well, we all write it as ds squared. So that's minus c squared t squared plus dx squared. And this is what we do in space-time. And this is what Einstein did all those years ago back, 1905. I'm not going to do much in special relativity, but this is important. But I said that in cosmology, distances are moving away. So we write x. We factor out the moving, the scale factor, a of t. So in cosmology, this ds squared becomes ds squared is minus c squared t squared plus a squared as a function of time times dx squared. And this is called the Freedman-Robertson-Walker metric, or for short, FRW. We can draw a space-time diagram. Obviously, I can't draw in 3 dimensions. Actually, I can't draw, so I stole this. This is called a space-time diagram in 2 dimensions. Here we've got CT, and here we've got the distance. If we're here, then light would move up this path. This is the path of a light ray. And this region, this is the future light cone. And this is our past light cone. So this is the distances we see back in time. And if I throw a tennis ball, the tennis ball does not move on this path. It'll move inside this future light cone because its speed is less than that of light. You don't know how fast I can throw. Yeah, that was a joke. So how do we know that galaxies are moving away? We know from their redshift. I think you all know the Doppler effect. So we can define the redshift, 1 plus z. Z is the redshift. It's the wavelength observed over the wavelength emitted, or the scale factor observed over the scale factor emitted. And we can see from the spectral lines the redshift of galaxies, of distant objects, so we can see from their redshift their distance. Now I can use this to derive the basic equations in cosmology. The basic equation is called the Freedman Equation. Ordinarily, you would actually derive it from Einstein equations, but there is a way of deriving it from Newton's equations, and I am going to derive it from Newton dynamics. I've left out a couple of steps, but we could fill them in. We start with Newton's theorem. What Newton's theorem says is the gravitational force of a spherically symmetric object with some mass distribution out to some distance r is as though all the mass were concentrated in the center at r equals 0. The other theorem we need is Birkhoff's theorem, and that's saying that if you've got a spherically symmetric mass distribution, the gravitational force of a particle at r equal capital R is due entirely to the mass inside the object. So here we have the uniform mass distribution. It's got density rho, distance r. Newton tells us that everything is coming as though it's at r equals 0. Birkhoff tells us that the gravitational force is for some distance is all coming from this r equal r mass. And the mass is, of course, the integral of the density times the volume. Okay, we can now derive the Freedman equation. The kinetic energy of a unit mass, so mass is 1, kinetic energy is a half r dot squared. What's r dot? Well, it's dr by dt, but what is that? I said that distances were a of t times x, the co-moving that goes with the flow. So this must be a half a dot squared x naught squared. What's potential energy? We know what the Newton potential energy is, minus gm over r. So that's minus 4 pi g rho r squared for the symmetry. What's r squared? R squared is a squared a naught squared. That gives me this. Okay, so I've used Birkhoff and Newton. Now, energy is conserved. We conserve the total energy, the kinetic plus the potential. So this is a constant. What is it? A half a dot squared x naught squared minus 4/3 g rho a squared x naught squared is a constant. I have called this constant minus k c squared x naught squared. That's for dimensions. Let me now divide through by a squared, and all of this depends on x naught squared, so I cancel this off and rearrange. And I now get an equation, a dot over a all squared plus k c squared over a squared is equal to 8 pi over 3 g rho. And this is an important equation. It's called the Freedman equation. K is a constant it determines the curvature of the universe, the actual geometry of the universe. K could be positive, negative, or 0, and that depends on precisely the density in the universe and will determine the eventual fate of our universe. Now, I can also derive an equation for the conservation of matter. I haven't put the steps in here. I guess we could derive this actually if we've got time at the end, or we could discuss it in a discussion session. The conservation equation is that the d rho by dt, rho dot, is minus 3 a dot over a into rho plus pressure P over c squared. From this equation and this equation, I can derive the third equation, called the acceleration equation, or the Chowdhury equation. So that's a dot double dot over a. So you just literally take the derivative of this equation, substitute for a dot when you've done that there, and rearrange, and you get this as minus 4 pi g over 3 rho plus 3p pressure over c squared. Is there a question? Can you shout, please? Sorry? No. Oh. Oh yeah, well, just say k is equal to 2k. It's a constant, right? I'm sorry, yes, you're quite right. Gosh. Okay. Yeah, there's a 2 missing, I'm sorry. Ah, that's from the original notes. Since we'll set k equal to 0 in a minute, it doesn't really matter, but thank you. Okay, so look, we've now got 3 equations. From these 3 equations, we can analyze the behavior of the universe, or the dynamics. What we need to do this is what's called an equation of state. This is the behavior of the pressure as a function of density. So if we write P as P of rho, and so that is omega rho c squared. The c is there for dimensional grounds. Omega is a number. And we can play with that number. If omega is 0, we have pressureless dust. And this is like the matter in the universe. If omega is 1/3, this is a universe dominated by radiation, light, electromagnetic waves. Where does that actually come from? This comes if I had been able to tell you what the energy momentum tensor is. But since I only have 4 lectures, I can't go into that. It's not completely mysterious that omega is 0 or 1/3. It's coming from actually analysis of the energy momentum tensor, which has both pressure and density in it. And that's an aside. Is Gaza still with us, by the way? Okay, good. Now, if we look at a matter-dominated universe, this is the original Einstein-de Sitter universe. Here, we set k equal 0, so it doesn't actually matter that I skipped a factor of 2, but thank you for that. So it's a pressure-free dust universe. The pressure is 0. So now, let me go back. P is 0. Where is it? There. So we can solve this equation. Integral rho dot over rho is integral a dot minus 3 a dot over a. The time it takes me to do this, I think you solved it in your head. Challenge for you. So solving that little equation, no, you didn't, did you? Gives rho is rho naught, some constant, over a cubed. That tells us that the density in the universe, when it's just got dust, matter, is going as 1 over a cubed. I now shove this into Freedman equation. So I now put that, I substitute rho naught over a cubed and solve this equation with k equals 0. Simple equation to solve. And that gives us that A is going as T over T naught. T naught is today to the 2/3. That tells us how we expand. And here you've got what T naught is. And T naught is 2/3 H naught inverse. H is A dot over A. So H is 2/3 T. T-thirds over T. And rho, therefore, is rho naught, T naught over T squared. And this is the Einstein-de Sitter universe. It's a good approximation to our universe today. A very good approximation. And up until the end of the last century, we thought it was actually our universe today. If we have the radiation-dominated universe, this is the Tolman universe. So let me go back. This is the universe where omega is 1/3 in here. So P is rho over 3. So P is rho over 3, so this is 4/3 here. So rho dot is A dot over A rho over 4 A dot over A rho. So we can solve it. And what we find, rho is rho naught over A4, which I think you could all do as I was saying it. So it's rho naught, T naught over T squared, and A is T over T naught to the half. Okay. This is the main contributions in our universe. With radiation and matter. And what you should notice is that radiation expands less slowly than matter-dominated universe. So what does that mean? If there's any radiation in our universe, it would have been expanded. but it would have dominated at an earlier time. We can see that, remembering that Freedman equation, H is A dot over A, the matter-dominated universe. To solve it, rho matter is 3h squared over 8 pi g, which is 1 over 6 pi g t squared. Radiation, 3 over 32 g t squared. Rho radiation over rho matter is 1 over A, the expansion. A depends on time. So if we go backwards in time to t equals 0, then this blows up. So if we start at earliest times, the universe must have been dominated by radiation, and at late times, it must be dominated by matter. And this is a very bad diagram. Since I don't know how to do them on the computer, I drew it. You note my nice straight axes. So here's density, here's time. Here we've got the radiation going as A to the minus 4, matter as A to the minus 3. And at some stage, these two diagrams must cross. This is at time t equality. We can actually go back now and work out that time when matter and radiation were equal at t equality. I'm not going to go into the details of that, but we can figure it out. And now we've got log A against log t. Very early times, A is going as t to the half. Later times at t to the 2/3. We have the radiation era and the matter era. In this era, in the radiation era, we formed the light elements. In this matter era, we form the galaxies. Ugh, I've gone much too fast. Have I gone too fast? Yes.
We can always talk a little bit early and give us some questions.
Okay, well, I have an equation. I have an equation here. Rho dot is minus 3 A dot over A, rho plus P over C squared. How do we derive this? How do we derive it? What do we need to derive it? What do you think we need? So let's have volume. What's volume? Volume expands. How do I write it? How do I write the volume? Would I write V is V naught times A cubed? Would I write that? I think I would, wouldn't I? And let's put this down as T. Be careful. So V dot is 3 A dot times A squared V naught. Okay. I've just done something sneaky. So V dot over V is 3A dot over A. Correct? What's the energy of a fluid element? So what do? Rho of T, C squared for dimensions. Okay. So E dot, rho dot, V dot, and there. So rho dot is equal to one upon V beyond the horizon. Okay. Guess what? We have no board wiper. Just gone beyond the horizon. It's okay, it's coming. Thank you. Okay. Board wiper. Okay, so. Hi. We don't actually know whether our universe is flat or not. But okay, as far the current observations have for a very long time suggested that K is 0. So the universe is flat. It's actually quite fun to put either K is 1 or minus 1 into those equations to solve them. And the reason is that you get different models of the universe. It depends precisely on how much matter is in the universe. I'll do this in the next lecture, whether you've got the critical matter, whether K is 0 or non-zero. And if there's too much matter, what you do, then K is plus 1, and you've got a closed universe, so it expands and then collapses. And you get a big crunch. And it might not be nice to be around at that time, but it's quite fun to solve. I mean, yes, people thought we had, that actually we had a flat universe, but I think it looks that way. Most observations suggest that, and that's what we really assume, to be honest. But we can play with model universes. The thing is that we keep getting more information and we put them in. And what we are determining is that it looks as though we've got about 5% of matter in the universe coming as ordinary matter. The protons, neutrons, radiation. About the 5% is about 70% of the matter is in what we call dark energy, and about 25% is in what we call dark matter. Now, they've both these two components have got this mysterious word called dark And I think there's a camera here, and I need to be by it. Oh, I see, okay. It's got this mysterious word called dark, and that means that we don't know what it is. So we know there's dark matter because when we look at galaxies, we see the galaxies moving. We can measure their luminosity, and we can measure how they go round each other. It's called rotation curves. And for years and years, we've known that it appears the galaxies are more massive than the light we're receiving, much more massive. There's very early work that goes back to, was it 50s or was it 60s, by Vera Rubin, actually it might even be 70s, by Vera Rubin, that accurately measured the rotation curves of galaxies. I should say Vera Rubin did this fantastic work. She never got the Nobel Prize, got a hell of a lot of recognition from some sections of the community, but never a Nobel Prize, and unfortunately she died a couple of years ago. They measured the rotation curves and found that there's much more massive than the luminous light. So we know that there's this dark matter. We don't know what it is. And our attempts to go say, well, it could be a fundamental particle that doesn't interact with light, so we wouldn't see it. One line of observation is that it's tiny black holes called primordial black holes. But the jury's still out on what dark matter is, but we know it's there. We've recently, since the late 90s, seen that the universe appears to be undergoing an accelerated expansion today, not moving with constant velocity, but increasing. We got this from supernova results, and now it's consistent with more accurate observation. We still don't know what is going on there. It could be some constant that appears in Einstein equations, and I haven't put into Freedman, by the way. We call this, but we've dubbed this dark energy. And, you know, it's still a factor that seems to be there. And precisely how much dark energy, dark matter, and ordinary matter will determine the ultimate fate of our universe. I mean, I've tried to understand dark energy. I have models of it. But models are great fun to work with, but they're not really giving you the answers we're looking for. And what I suspect is going on is that we don't understand how general relativity and quantum mechanics interact. But I can't do it. I can't do any more than that. I don't know if I've answered your question or not. I might have given you too much information. So I was just going to sort of tell you that I've now got, bunging that together, so we've now derived that equation. Now let's assume that we have uniform pressure and adiabatic expansion. I think you've all done some sort of kinetic theory. So first law of thermodynamics, dE is minus P dV. Okay, so E dot would be minus P V dot. What does that give me? Putting this all together gives me the equation. What I call the conservation equation, minus 3 A dot over A rho plus P over C squared. There we go. Now, deriving the acceleration equation from Freedman equation and this is absolutely straightforward and takes 2 lines of algebra. I'm not doing them. You are. Do you all know how to prove Newton's theorem? How many know how to prove Newton's theorem? So Newton observed what? The gravitational force from a spherically symmetric mass distributed out to some distance r is the same as if all the mass were concentrated at the center. How do we prove that? How would we start by proving it? What would we start with? What do we know? What's the Newton potential? Do we know the Newton potential? Yes, we do know. Yes, yes. 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 You know it. Okay. Sure. You know it. That's it. I mean, what do... I'd love to be able to put this down somewhere, but... Okay. If you consider a spherical shell, at r equal r, then we've got some element, ds. What's that? So radial part, r squared, sine theta d phi. And what other equation do we have? Newton, maybe. The potential. And is that correct? No, it's incorrect. There's a minus sign. So this is the Newton potential. And I mean, this just gives me Newton's laws, right? That so Newton potential phi Okay, that gives me, I can now write an equation. That the integral del phi dot ds sine theta d phi. Okay, I can do this integral. 4 pi r squared r double dot now I can use what I had before. What did I just use for that? Oh yes, I just used the definition of the mass. So for a point source, r double dot is minus gm over r squared. As for point source, and there's a sign mask gone missing. So Newton seems to be correct. And this is I can't prove from this Birkhoff, but you do a similar proof. That you just assume that everything, all the gravitational force is just coming from that sphere inside r equal r. And you can assume it's concentrated at r equals 0. Simple. So we've got two simple theorems that lead to those lovely theorems in those lovely equations in cosmology. And I think I'm nearly to the end.
So, in that case, maybe this is a good time to ask everyone any further questions on the material? Anything? Oh, yeah.
Very good question. It means that it should approximately expand at constant velocity forever. I could draw an approximate equation, approximate diagram of how the universe might expand. And I'm going to do this tomorrow. I could have shoved in more material. Maybe I will tomorrow. I think you know that the universe starts with a Big Bang. So I could have a model of a universe where it expands out to some critical value, then collapses. I could have a model of the universe where it sort of expands like that, or like that. This is what we call the flat universe. This is the open and closed. And this just depends on the matter content in the universe. Yeah. Yeah. I mean, doing is that we're trying to understand really some very deep questions. I mean, some people think that we have a model of the universe that would look a bit like this. A sort of bouncing universe. And you can get this from some sort of string theory, where you get down to a very small distance and then expand again. But it's not a very popular view, actually. What's interesting is that Robert Dicke, who was one of the greats in general relativity in the early days, actually had a bouncing universe model. Yeah. I've no idea if it works or not. Entropy. Yes. Look, I mean, we know the laws of thermodynamics. And the laws of thermodynamics hold. What I don't know is what would happen to thermodynamics in that case. But yes, entropy increases. But are you concerned that as you start to collapse, it looks like we're going to a more ordered universe?
Maybe another cause for concern maybe is when you wrote dE is TdV, you just left off the term, right? TdS.
Oh, I'm sorry. Yes.
But I also always leave off that term, but I've never worried about it. Maybe you can explain.
I don't think for this particular application that term TdS is important. I'm sorry, yes. And actually, that's clear. It's not important for that particular case, but I can see that there could be a fundamental importance in a quantum mechanical universe. Yes, good question. Sorry, I didn't realize that was what.
We have time for a few more. So any other questions?
Yes.
But it's clear it's not symmetric at every scale, right? So what evidence or...
Okay. So one can derive the Freedman equations assuming Newton's theorem and Birkhoff's theorem, and we have symmetric distribution of mass, density. Now, actually, the universe, we do have approximates. You know, if you're looking at this from outside, at some distance, the matter in the galaxy, say, is approximately symmetric. If you're some distance away, you don't see the clumpiness that we see globally. But if you were wanting to really derive Freedman equations, you would start from Einstein equations. Since I cannot assume everyone has done general relativity, I can't start there.
But you there also assume symmetric distribution?
No, you just take the derivatives. No. No, Einstein equation does not. But we can understand how you would derive a Freedman equation for the universe using just classical mechanics, but it's a nice derivation. But if you want to go deeper than that, you have to go to general relativity.
Other questions?
Oh gosh, not you. It's not on.
I think I'm not.
It's either not on or there's no battery.
I was very loud. You said that our universe changed from dominated by radiation at early times.
Yes.
When the light elements were formed, and now we are at the time of dust.
Yes.
Could you give us a little bit more insight what happened? Is it really the change of energy of radiation that was converted into matter? What happened in this time?
Yes. So the universe would have started really small and expanded. And as it expands, it cools down. There's actually, I'm going to do it next time. And eventually, the radiation is expanded away. And then the matter is then the dominant force, the dominant matter in the universe. Quite a lot of physics happens at very early times in this radiation universe, when the universe would be very, very hot. And there's a hell of a lot of going on at very, very early times. I mean, you start with the universe being really tiny and really hot. And at some stage, as the universe cools a bit, now let's backtrack. So originally, we could imagine that the only particles that we had was radiation, loads of it, electromagnetic radiation, and quarks and leptons. So quarks, electrons, muons, neutrinos. As we cool, you start to, the quarks start to coalesce, and you go through what's called the Qcd transition. So the quarks would form protons and neutrons. And then you cool a little bit more, and the protons and the neutrons start to capture electrons, and you form hydrogen. Then you form hydrogen, you can start to form deuterium and helium, and also lithium. And that happens within the first few seconds. How do we know that? Because there's a relationship between time and temperature that I haven't produced. And then eventually you cool down. And I mean, at this very early time, the matter is still ionized, and it's, thick soup. And eventually everything decouples, and photons just come to us today, and matter dominates. I think there's, does that thing work?
Okay, but before taking this question, let me say one thing. I'd like to ask our colleagues in Gaza if they have any questions. Please write them in the chat if you have any questions. So thank you. And in the meantime, let's take one more question here, and then we'll come back.
Okay, I'm wondering if we can consider K as a variable, not a constant.
Yeah. I'd like to add some cosmological constant, but I haven't done. K just gives you the curvature. The cosmological constant comes in a slightly different way. I mean, you can just add a constant to those equations. I haven't done, but I will put it on the next transparency.
Thanks. I have a very specific question about the first equation on the slide that is there right now, about the last step that happened, because what I see is you factor out x naught squared, but I see there's an a and an a dot in the rest, and I wonder how, like, in my opinion, this should be a function of time then, no? So what is left is only constants. You know what I mean?
Not quite. Do you mean this one?
No, the on top.
On the top?
So I see you factor out x naught squared, right? And then there's like a sum of something a dot squared and a squared, and they should be function, like, at least one of them should be a function of time, no?
Yeah, but all I'm doing there, I thought that was right. So, what we've got yeah? Okay, so
Yeah, I get it. Thanks. Yeah, I see I see where was the mistake that I made.
is that
Thanks.
okay?
Yeah, yeah, it is.
Maybe we'll take one more question, if
Anything
anyone.
coming through from Gaza?
Yeah.
No.
I think they're following though. Yeah, yeah. So,
Okay.
good. Okay. So there'll be opportunities later. But any more questions?
You don't have to.
Yeah. Okay. In that case, let's thank Anne again for a wonderful first lecture. Okay. So now, before we break, I'd like to do something. What we're going to do is we're going to have discussion sessions, as I mentioned. For those discussion sessions, we have to break into groups. There are a total of 6 of us who will be running discussion sessions, which means we all have to count off in units of 6. So let's begin here and move that way. So, good. No. 3. 4. Good. 5. Good. 1. Yes. Excellent. Okay. Good. Not you. Okay. Everyone, remember your number, everyone. Yeah. Good. Okay. You're 2. 2, right? You're 1. You're 1, right? Yeah. 1, 2. Good. Okay. So maybe you could be 1 unit. Okay. Also 2 then. Good. Good. Okay. We're good. Missed the line. Yeah. 5. Okay. Good. Good. Okay. 1. Then yeah. 2. Good. 4. Okay. Good. 5. Okay. Okay. Sorry, I couldn't hear. Yeah. Guest. Okay. But again, you'll come to the session. So 2 of you together then. 6. Good. 1. Okay. Good. Good. 1. Okay. Yes, then you. Yeah. Okay. Okay, good. Everybody remember your number, okay? Okay, good. Okay, so that's all for now for the first morning session. So now we're going to break. There are some refreshments outside, and in a few minutes, lunch will arrive. And then we'll eat lunch. We will start again, I believe, at... We will start again at 2:30. Okay? So 2:30 we start again. In the meantime, food will be here soon. Okay. All right. Thank you, everyone. Enjoy.
اسمها روتيشن كيرف. طب تعال هيو ديسكشن هاي فاضي شغلوه.
الأمانات مكشوفة بس شو بده يودينا هلا على بداية الجامعة عشان